Now we come to the second question related to weighted graphs. And that is to find the shortest path between two given nodes. So we don't care about visiting all the vertices. All we care about is finding the shortest path through the graph from one point to another. So I've got an example here that I'm going to use to set this up. And I'm not going to show you Dijkstra's algorithm just yet on this first example. This first example, I'm just going to kind of show you one way to think about it, which does lead into Dijkstra's algorithm, but I'm not going to show you the exact details just yet. I'll do that on the next example. So here, our goal is to get from A to Z as efficiently as possible. So we're going to start here and try to end here. Now you could do this by brute force. You could just look for all possible paths from A to Z, but with more nodes and more connections, that would quickly become really painful to run. So here's how we think about this. We think about starting at A and then kind of radiating outward from there. We want to find what's the shortest path or what's the closest node at each step. So let me illustrate what I mean by this. The closest node to A, we have two options. It could be either B or D, but of course since the distance to D is only 2 instead of 4, we know that D is shorter, or D is closer. So A to D is the shortest one hop you can take, and that is a distance of 2, rather than from A to B, which would have a distance of 4. So that means D is the closest after one step out from A. Then we're going to look for the next closest, the second closest to A, and it should be clear that the next closest is either going to be B or E. In other words, since D is the closest to A, the next closest is either going to be the other one that's connected to A, or it's going to be one that's connected to D. So once we have A as our starting point and D is the closest, the only candidates for the next closest would be the ones that are connected to one of these two. And since the only two options that are connected to either A or D that we haven't considered yet are B and E, those are our two possibilities for the next closest. So the next closest could be from A to B, or from A to D to E. Now notice you could also get to E passing through B, but that's not going to be an option for the second closest because B would be closer to A than that. So we know that we don't have to account for the possibility you go A, B, E to get the second closest. Hopefully that made sense. But there are two options, passing through D to get to E or going straight to B. And of those two, going straight to B has a distance of 4, and then going A to D to E has a total distance of 5. So that means B is the second closest. Then the third closest since we've covered A, B, and D, the options for the next closest would be C or E. In other words, everything that's connected to B or D. So if there was anything else connected to A, that would still be an option for the next closest, but we've covered everything close to A. So the next level out is going to be one of the ones connected to the current two closest to A. So that's going to be C or E. And notice that we can have, coming from B, we can have two options, and then coming from D, we can have one option. So there's 3 possibilities for what the next closest stop would be. So we could have A, B, C. We could have A, B, E, or we could have A, D, E. And we just account for the cost of traveling to each one. A to B to C has a total of 7. A to B to E has a total of 7 also. And A to D to E has a total cost of 5. So that means E is the next closest by this route, not by this route. So we've got kind of radiating outward from there, and then it should be clear that at the next step, if we keep doing this, we're going to get to z with one more total added to our weight, one more weight added to the total cost. So that means the shortest path in total is from A to D to E to Z with a cost of 6. So that kind of gives you a sense of how Dijkstra's algorithm works, roughly speaking. And I'm going to show you a little bit more specifically how the algorithm is run in just a minute. But that's kind of the sense of how it works. You start at your starting point and then count the cost to the nodes that you can travel to in one step. And then from there, count the cost to the next level and the next level and the next level until you encounter your final point, and then you can stop. So I'll give you a sense of the more general version of this in the next example, but this at least kind of gives you a sense of how this works. When you go to actually code this, for instance, you need to have a very specific way to write the algorithm down, and that's kind of what we're going to get into in the next example. But this at least gives you a sense kind of how it works, and we can see that getting started. So in the next video, I'll show you the more specific description of Dijkstra's algorithm.